All right, so in this problem, we're asked to use a known power series to find the power series for a new function. And the idea behind doing that is we've got a couple of other techniques. One of them we've already seen is that we can just do a substitution from one into another to find the power series expansion. And we've also seen that we can add or subtract power series in order to get power series expansions of functions. And so here, the last kind of two techniques that we'll see to obtain new power series expansions really have to do with differentiation and integration. So what are these two properties? So in particular, what we can do is that if we're given a power series and we know that thing has an interval of convergence from a minus r to a plus r, so this is a power series centered at a, it's got a radius of convergence of r, then what we are able to do, if the function that this represents is going to be a differentiable function, and that function is differentiable on the interval of convergence for the power series, then it turns out that we can take the derivative of the power series kind of term by term, just using our power rule, and that power series will also converge to give a representation of the derivative of the function. And that derivative and that power series expansion will still continue to be will still continue to give the function value on the same interval, so we don't lose any values in our interval of convergence. Now, kind of likewise, in that same notion, we are able to take that power series and we can integrate term by term. So we can just use our power rule for integration, and that will also give us the integral of the original function as a new representation of a new function, the integral of f of x. And just like with the differentiation, we do not lose any values. We maintain the same interval of convergence that we had for the original power series. And so kind of the punchline is we can differentiate term by term, and we can integrate term by term, and it maintains the same interval of convergence as the original power series. So that's a pretty powerful, two really powerful techniques that we can keep in mind, and that's exactly what we're going to use in this case. So basically, we're going to take the power series that we have. So we've got the power series natural log of 1 plus x, and we know that that thing is going to be n equal 1 up to infinity of minus 1 to the n plus 1, x to the n over n. Well, if we take the derivative of both sides, so the derivative of the natural log of 1 plus x, then that's also going to be the derivative for the power series taken term by term. So that's going to be the derivative of the minus 1 to the n, x to the n over n. So our coefficients just depend on n, so those are just constants. We pull them to the outside. So on the left-hand side, we take the derivative of natural log. We have 1 over 1 plus x. And on the right-hand side, we have our sum, n equal 1 up to infinity, of, we use the power rule, so we've got a minus 1 to the n times x to the n minus 1 over n. And so what happens, our n's cancel out in this case, so we have a power series, n equal 1 up to infinity of just minus 1 to the n, x to the n minus 1. And so this gives us our new expansion for our function 1 over 1 plus x. Now, we could also have gotten that expansion by just doing a substitution on our 1 over 1 minus x, but here we've kind of done it both ways, and we see that we end up with exactly the same power series expansion. And so what do we know? Our answer then is just going to be minus 1 to the n, x to the n minus 1.